Welcome everyone, and I thought this was an excellent physics torque problem, so I wanted to analyze it and show it over YouTube to maybe help out some other people who are having troubles with torque. Essentially, this problem is extremely easy. The only difficult part of this entire three-step problem is geometry. Let me show you. So it starts off extremely simple with a horizontal board. So part A says, two people, call them left and right, will carry a long flat board of length L and 250 Newton weight. They will do this by lifting straight up at opposite ends of the board. Find the force of the left and the force of the right. So what do we know? We know that the net force on this board is 0 and the net torque is also 0 because they just have it lifted. They want to keep it in that equilibrium. So when your net force is 0, you obviously make a full body diagram, but they have one right here for us. We can really represent the force of gravity as, oops, that's a terrible line there. There we go, that's much better. As you know, being at the center of the board, just directly down. So if the net force is 0, we know that 0 is equal to the 250 Newton force, which is acting down, so we can represent it with a negative, plus the force of L, plus the force of R. So what do we know then? We know that 250 newtons is equal to the force of L plus the force of R. Then we also have this piece of information that we know. We know that net torque is also 0. So if we look at this, we can take torque with respect to force L. We know that force L kind of comes out here, and it also comes out here to force R. We know that the force of R is making it turn this way, while the force of gravity, we call this the force of gravity, is pushing it the opposite way. So we have 0 is equal to the force of gravity is, well, we're going to represent the force of gravity with, or the torque of the force of gravity with a negative. So negative 250 Newton times L over 2, because its length is L, the board's length is L, and we see that it's acting on the middle point. So it's L over 2 distance away from the place that we're representing, or we're taking our torques from. Similarly, the force of right can be represented like this, times L. With a little bit of math, you see that it's 125 newtons is equal to the force of R. And if we look back here, we see that force L must therefore be equal to 125 newtons as well. That was simple. Let's see what happens with part B. Part B says, again, two people will apply a force straight up at opposite ends of the same board. But this time, one person is short and the other is tall. Because of their height difference, the board is tilted at an angle of 36.87 degrees. Find Fs and Ft. So once again, we have gravity acting at the center, straight down. Once again, let me fix that. There we go. Force of gravity is equal to 250 newtons. And once again, we have the sum of the forces here. They're all acting in the y direction. So 0 is equal to negative 250 newtons plus force F, or the force of the force S, plus force T. So we have 250 once again is equal to force S plus force T. Now torques is where it gets a little bit more challenging. You see that 0 is, well, once again we're gonna take torques with respect to the force S. So force S comes along here. This is its R, and this is its R. So we have force T acting, trying to go this way, and we have force of gravity trying to go this way. So now when you take torques with an angle, the general equation is torque is equal to R, which is the distance, times the force, and times the sine of the angle between the distance and the force. So if this is our distance right here, and this is our force of gravity. Our angle is going to be this angle, and our angle over here is going to be this angle, because it's acting to go this way. So it's acting right here, and on this angle, while gravity is acting here. We look at a triangle like this. This is to represent the force of gravity. So we see that the force of gravity is here. We know this angle is 36.87. We know this angle is a right angle at 90 degrees. So this angle right here must then be 90 minus 36.87. And thus, if we have 180 degrees total from here to here, this angle must be 180 minus 90 minus 36.87. So with that information, we can see that the R for the force of gravity is still L over 2. The force is still 250, and now the sign is actually, well, 180 minus 90 is just 90. 90 plus, and then the double negative makes it a plus. 90 plus 36.87. And then once again, this is acting in the, what is this, the clockwise direction, so we're going to give it a negative. And now we're going to look at our force T, or our torque T, really. So that's positive for the torque of T. We know that, we don't know its force. We know that its distance is L. And now its angle is going to be, well, this is a big right triangle here. I don't know if you can see it with all the mess here, but you have the right triangle here is 90 degrees, 36.87, so this is going to be 90 minus 36.87, because we know that there's 180 degrees in a triangle. This is 90, so it'll be 90 minus 36.87. That should be a minus. Okay, so, some simple algebra here. We see that 125 times the sine of 126.87 is equal to the force T of sine, what's this? So that's 4, so we got 54, so 53.13. And now from here we can use a calculator to find out that force T is equal to 125 Newton. Similarly, with this equation, force S must also be 125 Newton. So that's a little interesting. We see that the angle changed, but it had no effect on the actual force of the two individuals here. Now let's see what happens with a box instead of just a horizontal plank. Okay, so this one says, this time the short and tall person are carrying a large uniform box of length L, height equal to half the length, h equals L over 2, and weight 250 Newton. The forces are still straight up and at opposite ends of the length. Find Fs and Ft. Okay, well, once again, we know that 250 newtons is equal to force S plus force T. Same operation as before, just continuing forward. The interesting part here is torque. We know that the center of gravity is right here. We know that there's a force of gravity being applied here. So that means if we take torques again from the bottom left corner, we now have this triangle here formed. So we see that it's 36.87 here. So we'll start with the torque over here. So we have 0 is equal to, this is torque, is equal to that. So if we look at this one, we're going to start with the force of T. We have L, because this is the distance to the force of T from the point of interest of our torque. L times force T times, once again, sine of 90 minus 36.87. Okay? And now there's obviously the clockwise torque being applied here at gravity, so that's minus. We know that the force is 250. Now what is the distance and what is the angle? Well, we're going to have to do some work here. So this triangle that I kind of tried to represent here, we see as a right triangle. We need to find its hypotenuse for the length, because that's the length between between our torque that we're taking with respect to F of S and our center of gravity, which is being applied. The force of gravity is being applied here. So we have our triangle. What's this distance? This distance is L over 2. Right here is L over 2, and this distance is actually L over 4. So we have L over 4 and L over 2. Using Pythagorean's theorem, we have the square root of L over 2 squared plus L over 4 squared, which simplifies to the square root of L squared over 4 plus L squared over 16. This just becomes 5, square root 5 times L, all of that over 4. So that's the distance. That's the hypotenuse. So we have this, times it by square root 5 L over 4. Now the sine, we have to do some trigonometry, some geometry here again. So we have, this is what we're looking for. This angle here. So we know that the center, or the force of gravity is being applied here, straight through here. So this whole entire angle is 180. So if we can get this angle, we will know what this angle is. Well, so using our triangle once again that we have over here, I'll redraw it. L over 4 and L over 2. We're wondering what this angle is. Well, we can use trigonometry. The inverse tangent of L over 4 over L over 2 will give us the angle that we're looking for. Well, the L's cancel out, and it just becomes the inverse tangent of 1/2, which is equal to 26.57 degrees. So with this information, we have 26.57 degrees. So we see here that we have a 26.57 degree angle. We have a 36.87 degree angle. The force of gravity is not on the same line as the triangle here. Instead, it creates a new triangle. Let me use a different color to show you what I mean. Instead, it creates this new triangle that goes from here straight downwards here, and this is the force of gravity. So the angle we're looking for is this one. We have this angle now, which is 26.57 plus 36.87, which, let me do that calculation on a calculator real quick. 0.57 plus 36.87 equals 63.44. So now let's take a look at this triangle, put it up, let's raise it up here. So this triangle is actually so we got what, 63.44 was it? I think so. 90, and this one is obvious, must be 180 minus 90 minus 63.44. So that's just 26.66 is this guy. So we know that this is going to be here, so now we can simplify things greatly because it's just 180 minus 26.66, which is equal to 1 153.44, and that makes sense. It's a large angle. So we go back up to here, and we see that it's 153.44. So now we have this business equal to this business. Let's simplify it. So the L's cancel out. The 250 goes to the other side. Okay, so let's take it down here. So we got 250 over 4, which is just, we'll just simplify it to 125 over 2 for now, times it by the square root of 5, and then we got all of that business there, sine of 153.44, all of this over the sine of 90 minus 36.87, 90 minus 36.87 is equal to the force of T. Let's make sure I didn't forget anything. Got that accounted for, boom, boom. It looks like we're good. This comes out to be force of T is equal to 78.1 newtons. The force of S, therefore, is equal to 250 minus 78.1, which is equal to 171.9 newtons. So it's interesting that when it's a box and not just a flat rod or flat plank, that it does matter which side of the angle you're on, or which place you're on. Yeah, if you're the small guy, the short guy here, you're going to have to use more force than the guy up here. Thank you for watching.